much for the introduction. Let me share my right screen. That will work. Okay. Everyone can see this okay, I assume?
Yes.
Okay, perfect. All right, great. So yeah, it's thank you so much for inviting me, and it's an absolute honor to talk to you tonight. Excuse me if I sound a little bit rough. I'm just recovering from the flu that everyone else has seemed to have. So I hope tonight that I'm going to be able to bring you into my world, which is going from single dish to interferometry. And this will be looking at very long baseline interferometry in particular. And I'm speaking to you from South Africa, so of course I have to put the Hotter Basic Radio Astronomy Telescope, which is about 50 kilometers from where I am at the moment. So for a little bit of context, I work at the University of Pretoria. I'm currently a senior lecturer here, but I'm also worked for the University of Manchester for the SKA, and I'm also co-chairing the SKA VLBI working group. So I hope that I can impart some of the knowledge that we're trying to build at the moment across to you guys, because it's important for us to get this outreach and tell you what's happening in the world of VLBI. So a little bit of the outline today. I'm going to give you a kind of an interferometry 101. I think you've had this before in previous talks because I've been watching the old videos. I think you had Leia teaching you this last year. So I'm going to try and do this from a different approach. I'm going to talk about what VLBI arrays today are doing, talk about some of the science that we do with VLBI, and then I'm going to touch a bit more on kind of the next generation VLBI, on the new telescopes and the new developments. And it was actually apt for me to talk to you actually today rather than last week, because I was just at a conference talking about new developments and new techniques in VLBI last week in Madrid. So I was hastily writing the rest of the slides today just to make sure that I could talk to you guys about literally the cutting edge of what's happening at the moment. So, of course, you know about interferometry before, but the key thing with interferometry was that we wanted to get high resolution. So this is the Robledo Deep Space Network Telescope. It's got 70-meter aperture, and it has about a resolution of about 1.5 arc minutes at a 3-centimeter observing wavelength. And if you take the tiniest refractor telescope in the Greenwich Museum, this has about a 2-centimeter aperture, and it has a 6 arc second resolution at 600 nanometers. So it was pretty, radio telescopes, of course, don't have good resolution. If we want to understand the inner workings of the universe, take an image of a black hole, for example, we're going to need to increase this resolution. So you can do that in two ways. You can reduce the observing wavelength, or you can increase the size of the aperture. And of course, people used to do this in the 60s and 70s, making bigger and bigger dishes like Arecibo, even though this doesn't exist anymore, with a 305-meter aperture, which has 25 arc seconds resolution at 10 gigahertz. But your human eye is just as good in terms of being able to resolve objects in the sky. And of course, you can go too big. And I think you all know about the old Green Bank telescope, where it went from this into looking like this, a bit of a pancake in 1988. So we can go too big. And of course, this necessitated the need for us to use interferometers, where we can instead replace that D parameter, the size of your dish, with the distance between the two telescopes, and we interfere the signals together, such that you now are not limited by the size of the telescope or the engineering to make that huge telescope, but the distance between the two. And this means that in principle, if we can do the technique well enough, and we've already done this and shown this before, you can put radio telescopes in space and get resolutions which are larger than the Earth's diameter. So we had this with Radio Astron, which I think died in 2018 with a 10-meter telescope out in space, allowing you to get micro arc second resolutions because you can make this B parameter so large. So I'm going to try and start talking about interferometry. I'm going to try and not make it too technical, but VLBI is known for being the most technical of all the interferometers. So I will have a go. But also, if you also have questions about things as I'm talking, please interrupt me rather than wait till the end, because then I'll also forget to. It's 2-year-olds does something to your brain. So by doing interferometry, of course, we can get this. This is the comparison of image fidelity that you get. This is Meerkat. This is our telescope in the Karoo Desert, 64 antennas here in South Africa. It's a beautiful place, but it's really, really cold and really, really dry. But you can make these amazing fidelity images. This is Fornax A, as seen in the radio. A nice supermassive black hole sat in the center of here. And you can see all of these filamentary structure of the gas. And this is the comparison image with a single dish. This is the Sardinia radio telescope at 6.6 gigahertz. And it's just pretty much 2 blobs with a bit in the middle. So you can't make much out here. So this is also key on why we want to use interferometers to make these amazing images. And this is one of the best images I've ever seen with an interferometer. So how does an interferometer work? Well, you can I always think of it in this way, and I always think of it, even though this is not technically true and the maths isn't true for this, conceptually, it's the only way that I kind of think of it. And if you take a parabolic dish, the idea is that if you've got waves that come in from infinity, as you can assume that most of your things you're looking at are, then as the waves hit the dish, and it's shaped like a parabola, it will always hit the focal point in phase. So i.e. the path from this point here, can you see my mouse on here? Okay, the path from this point here to the focal point is exactly the same length. And so that means that when you end up getting your waves coming together, you're going to get this red line here where it's actually at a maximum all the time. So this is kind of how an interferometer works, except that you're taking parts of that mirror and moving them apart. And you can make basically a virtual parabola, which is the size of the Earth, and you move these mirror segments apart, and then you focus those rays again, making sure that this path length is exactly the same. So you could physically pick up your dishes and move them into the sky thousands of kilometers, which wouldn't work, or you could just delay the signal in the electronics below. And if you delay the signal by the right amounts, they'll arrive to that focus position in phase again. And so as long as we know precisely where those segments are, and we know how far the signal is coming from, we can do and interfere the signals such that they constructively interfere. We get this red line where we keep our signal there. And you can do this either with electronics, or you can make the bit of wire a bit longer, so the signal takes longer to go through. And this is kind of how connected interferometers work. They have a thing called a correlator that takes the signal and combines them together such that they interfere constructively. And the one thing that's key in this is that you have to delay the signal by the right amount. So you can see this is the antenna 1 and antenna 2 in this diagram or cartoon. And you can see the waves are coming in coherently, so they all come in phase. And at this point, which is the dotty orange line, they're still in phase. So we've got a peak with a peak, so you'll end up with a signal that comes in, but you've got this extra path length which passes that down here, and you have to basically remove this contribution. Now, if you have 2 telescopes that you can see, you can basically work that out from a simple bit of trigonometry, essentially. It's good enough. So I could put a laser ranger on telescope 2, find the distance to telescope 1, and work out what this angle is to my source. The second thing that's useful then is that means that you can just calculate that, give it a delay, which is just this geometric delay, and the change in the difference between the wire lengths, how far they're going to go to your correlator, and you can correlate all of this in real time. You also have a clock, which is the same for everything. So you can just do it relative to some position on the plane, and you can assume also that your telescopes are on a flat plane, so that all the maths makes it so much easier. And once you have them all in constructive interference, you get your interferometer signal at the end. Now, the difference between this, and this is what we would call a connected interferometer, i.e. they're all connected by fiber optics, which goes to a correlator on site, which produces your signal at the other end, and VLBI is that VLBI essentially does not have, they're not connected in general. That's the best way to describe it. So instead with VLBI, we have this situation. So you have telescopes, they can be arbitrarily separated across the entire world, and they will be written, you'll write all of your data to disk. And at each of those telescopes, you will also have an atomic clock, which increases the cost. A normal maser, I just got a quote for one. It's about £500,000 if I got the quote for a proper hydrogen maser. And this only gives you errors to within 50 nanoseconds. And you have to have an atomic clock at every VLBI site, or at least very close to the VLBI site. And then what you have to do typically is you would take these my brain's gone there. You take the data, you'd write it to disk, you tell what time it is on the atomic clock, and then you'd ship it to a central location to process the data. So this could either be, there's a few places, the Netherlands, there's New Mexico, in Bonn, there's a correlator. And once you get it there, it's a lot more difficult to process the data. So the first thing you have to do is we have to align, or we have to synchronize the clocks. So every atomic clock doesn't tell the same time, which is kind of annoying. So we use GPS systems to be able to align this. So that takes your error in the signals from 50 nanoseconds to 5 nanoseconds. And then we still need to search for where we get that interference signal at a maximal. And we call this clock searching. On top of this, we also have to have a different delay model. We can't just use that assumption of kind of trigonometry, telescopes on a flat plane. We have to model everything. We have to model all the source positions, the station positions. We have to model different time zones. You have to take into account diurnal spin from friction. You got to take into account the tides. So whether the moon is above you or not matters, because that changes the position of your telescope by 30 centimeters. We have to take into account loading. If you've got, if you have too much water underneath you, your telescope sinks and the gravity changes the amount of time it takes for the signal to come through the atmosphere because of gravitational delays. So there's everything like this which affects your signal, and we have to model this. And these are all the different things on the right-hand side that goes into this model. So it becomes extremely complicated. And luckily, this is VLBI. You can turn it the other way, and you can actually work out this stuff using VLBI as well. You can turn the technique upside down to do this sort of things, and I'll talk about that a little bit later when I talk about Geodesy. Now, once you've calculated all of this, you normally have this in a big supercomputer. You can then do this searching, and you end up with these beautiful plots. On the left-hand side, we've got the same interference pattern. If I can stop this when it's at the maximum, then this is what you want to have. You want your two signals from your telescope in phase, and they combine to give you a maximal signal. And on the right-hand side, you can see the signal as a function. This is just a frequency, but channelization, I think. And this is in the email-in telescope. So this is Jodrell to Knockin, Jodrell to Defford, Jodrell to Cambridge. And the peak in the middle is showing us that we've got this sort of constructive interference happening in our signals from our distance source. And hey ho, you've got an interferometer. So I hope I haven't put you all to sleep about this. So this is our difference between our connected interferometers and VLBI, basically. And it's just the fact that they're separated. And we have to do some more careful bookkeeping, is the best way to describe it, and modeling for us to be able to get a signal at the end. So with all your telescopes synchronized, you're able to do stuff like this. You're able to combine telescopes around the world. And I hope this video works. Yes, normally doesn't work. And you're able to reconstruct images of extremely, extremely tiny things. So this is a simulation of the Event Horizon Telescope. The rotation of the Earth helps us fill in the information in an interferometer, and you start reconstructing the image as you move around the Earth. And you can see just how, if I just repeat this, You can see how as soon as we get more and more telescopes coming in, we start sampling. This is kind of your lens that we're filling in the holes with, where these colors are. And then when you try and make an image out of that, you start recovering what the source structure is. And the astonishing thing with the Event Horizon Telescope and these two images is this is basically equivalent of you taking a donut and putting it on the moon, and then you sitting in your back garden and imaging that. That's how small these are. So the left side, this is MED2, MED7, sorry. With this black hole shadow, the sort of brush marks are the polarization of the magnetic fields. And on the right-hand side is our own black hole Sagittarius A star, as seen with the Event Horizon Telescope. And this is sort of the pinnacle of VLBI at the moment. This is kind of the holy grail for our area. So if you say you do Event Horizon Telescope, you get lots of money half the time. So that's kind of, you know, where VLBI is at the moment. And the next part I wanted to go and talk about is just about the VLBI telescopes and the VLBI arrays that are here today. And it's a very versatile instrument. We have lots and lots of different arrays. So we cover frequencies now from 55 megahertz all the way up to 350 gigahertz. So we're looking at a large amount of different astrophysical phenomena that we can start looking at using this. At 350 gigahertz, you're starting to look at the dust emission. At 55 megahertz, you're starting to look at like cyclotron emission and things like this. And we can even do ionospheric studies of our own ionosphere using VLBI now. And it's currently, even with the huge square kilometer array, it still will have the largest collecting area of any instrument in the world. So these are ad hoc individual telescopes which combine together to make a huge collecting area. Some of the best or well-known ones are the European VLBI network. This is one that I use most of the time. It's not really in Europe all the time. As you can see, there's a lot of East Asian telescopes which contribute to this. But this telescope, you know, has some of the largest telescopes in the world. So that includes Effelsberg, the 100-meter telescope in Germany, Jodrell Bank, where I did my PhD sitting under that telescope. And new telescopes, especially in China, there's 65-meter ones, there's 500-meter vast telescope in China now, which all want to be part of these arrays. So this is huge collecting areas for us to look at the faintest things in the universe. On top of this, you've got the American Very Long Baseline Array, and this is extremely versatile. It's kind of 10 very large array dishes scattered across the US. And of course, we've got the Event Horizon Telescope, which made that beautiful image. And this is all possible because of the use of ALMA, which is the Atacama Large Millimeter Array, with its 66 dishes that all work as one as part of the Event Horizon Telescope. On top of this, we've also got kind of newer ones. While the Australian Long Baseline Array has been around for a while, but we've also got this East Asian VLBI network now. This is a fairly new network, which typically looks at higher frequencies. And a lot of their focus is on things like lasers, so microwave lasers, which look around high mass star forming regions. And there's a lot of development in this area. And China is currently building, I think, 4 or 5 new dishes across their country. And you also know about the International Low-Far Telescope, which I think Lea Morabito talked to you about last year. So I'm not going to talk about the ILT because you should be all experts in that, and you're probably more experts than I am. Yeah, David?
I also have read about the African VLBI network that's being built, and I wonder what the status of that is.
Yeah, I will come to that at the end for new telescopes. But the spoiler is there's nothing that's being built, but we're in the process of hopefully getting funds to build it. That's the best way to describe it at the moment. It's sort of hit a snag, the African VLBI network. So I'm hoping that in the next 5 years, we'll have something at least. Yeah, So these are the sort of VLBIs arrays that we have at the moment, and these are all doing amazing science. VLBI is really on a kind of renaissance, and some of the new developments that I'll talk about a bit later is helping this. And the big thing for VLBI, I know, has been looking at active black holes, at active galactic nuclei. And we know, of course, that these are intimately related. I think you've had a few talks on this before. And a key example of this is shown in the right. So this is showing some negative AGN feedback. In the yellow or the white is the optical. In the blue, you've got the X-rays, and in the red, you've got the radio emission. You can see these jets piling into the gas, surrounding the galaxy, and basically blowing these holes into the gas. And this heats up the gas, and anything that has hot gas typically doesn't want to go back to its host galaxy and then make stars. And when we look at statistical studies of this, you end up seeing an intimate relationship between the black hole and the host galaxy. So the mass of the black hole is proportional to the mass of the stars in the galaxy, or the luminosity of the galaxy. And one thing that VLBI is really, really good for is at finding these objects. So this is something that I do generally in my science area. And VLBI has the advantage is that radio can typically look through a lot of dust. We can look through a lot of dust, and we can start peering through black holes that are basically shrouding themselves from detection in other wave bands like the X-rays or in the infrared. And the advantage that we have with looking in radio studies is that we can basically trace both stars being formed and AGN at the same time. And this is typically or mostly extinction-free. And of course, with radio, we can identify the AGN via morphology. So you can see here on the left-hand side, you've got this. If you looked at this and you said, okay, there's a jet thing coming out, this must be coming from a black hole, then that's fairly straightforward. But on the right-hand side, many of our sources that we look at with radio telescopes look like the one on the right. 99.9% of these objects look like the one at the right. And you would never guess by just looking at this image, because it's a boring blob, that there is a black hole hidden in there. And you can see this here. This is a beautiful image of the deep fields as looked by Meerkat. And you can see the AGN in here, the kind of extended sources with the black holes. But each one of these kind of blobs over here, which you wouldn't be able to understand, which you wouldn't be able to not understand, you wouldn't be able to distinguish what's what so easily. If I zoom in, you wouldn't be able to say to me that there's a black hole in those objects without looking at other frequencies. So VLBI is really good at peering into these objects. And this is an example. This is our fluffy jet that we saw earlier. This is the VLBI image on the right-hand side. So it shows the bright, compact core in the center because of the high resolution that you get from VLBI. But likewise, with this boring blob, we can also do this to identify the accreting black holes. And this is partially one of the big science pushes that VLBI has, is to be able to find these objects hidden within these kind of complex systems, to say there is a black hole sat here. And now that we know that it's active, because it wouldn't make radio emission without it, we can start looking at how it interacts with the galaxy and its host galaxy, basically. So this is where the kind of modus operandi of VLBI is, but with the sort of, what's the right word? With the sort of new capabilities that we have, such that we've got VLBI arrays now having these huge collecting areas, and they're vastly sensitive. We're not just a detection instrument. We've got the methods to make absolutely beautiful images. And this is one of those beautiful images here. Oh, I've got a chat. Oh, that's just the central frequency. It typically gives us a bigger field of view. That's why we use 1.5 gigs. It's close to the 21 centimeter line, so it's easier for us to stay out of people's mobile phones and RFI. So we can make this beautiful image. You can see this on the right-hand side. This is a gravitational lens. And a gravitational lens basically is you've got some foreground galaxy. And behind this, you've got a background active black hole. And then as the the light passes through this foreground galaxy, it basically gets deflected and gets distorted. This image gets distorted and magnifies, and we end up with this sort of beautiful Einstein ring structure. And you can see on the axis, on the y-axis here, this is extremely high resolution. So, you know, this is kind of an arc second or two across, but the actual VLBI ring is just a few milliarc seconds across. Now, it may be a pretty image, but these sort of images are, because we've got this extremely high resolution, we can use these sort of images to start understanding the fundamental cosmological constants of the universe. Because this is very, very particular. The shape of this ring is very, very particular to how dark matter acts and its properties of the dark matter that's lensing it. So we think that there's currently 2 of these objects ever seen in VLBI like this. We think that if we can get 5 or 6, we'll have a sort of independent method for being able to calculate the Hubble constant going forward. Other things that we can do now with VLBI and has been done for a while is looking at nearby galaxies. I'm sure many of you have looked at M82 before. One of my favorites as well. So M82, of course, is the starburst galaxy you see on the right-hand side. We've got the Chandra in the blue, the HST in the green and the yellow, and you've got these outflows coming from the central starburst, coming from supernovae, and the winds coming from your high mass stars. And this is an image using the Very Large Array, a low resolution image, showing these kind of outflows coming from the center, along with the supernova remnants in here. And if we zoom into this and we use going from low resolution that we see here to higher resolution using our own UK telescope along with the VLA, we can get much prettier images. This is H2 regions with loads of embedded supernovae inside of here, but the supernovae still look point sourcey like. They just look like blobs in there. And so using VLBI, you can start actually probing and following the expansion of these supernova shells over time. So this is an example from Muxlow et al. 1986 with the same source, 1997, and Fenech et al. The same 2 sources, showing the evolution across decades of these objects expanding over time. And by measuring this and by measuring the expansion, you can start saying things about, okay, how did the supernova get all its energy from? What is the interstellar medium like? Because that will change the velocity of different components in these supernovae. What are the magnetic fields like? Because you've got to have synchrotron emission, you've got to have magnetic fields most of the time. And so you can do this for lots and lots of different objects and really look and have a deep dive into nearby galaxies using VLBI along with other wavelengths. So this top image is one of the most beautiful ones I've seen for a while. But there's a load of other science that we can now do with VLBI. As everyone aware of the fast radio bursts, I'm sure you've been trying to search for them in your data. I always used to flag these things out, I think, out of mine, because they look like mobile phone signals. But the one thing that VLBI gives you is that with these fast radio bursts, we can now localize the location of these to within regions in a galaxy. So before, when fast radio bursts first came onto the scene, they came from kind of a multiple degree area of the sky. But what we can do now with VLBI is we can actually correlate the position when we see a fast radio burst and say it's exactly in this part of the galaxy, which helps us actually understand what the origin of the fast radio burst, what the origin of the fast radio burst comes from. So you can see this here. This is FRB 180916. Good at names, astronomers are. But you can see that the VLBI actually points to this tiny, tiny region here, where this red dot is here. And this is a high mass star forming region in this galaxy. And this follows kind of what we think currently fast radio bursts are coming from, which we think are magnetars at this point. I got a message in the chat. Yeah, so VLBI angular resolutions. Yeah, pretty much. I can't remember what the Webb telescope exactly is. It's like 50 milliards seconds or something like this. So we can get around or better than that typically from the James Webb. So a lot of the work that we can do is complementary to the two. So the other things that we can do is we can look at protostar feeding. VLBI is very good at looking at masers. These are spontaneous, not spontaneous, stimulated emission in the microwave regime. And this is an example from Burns et al. So over here, we've got a protostar in the center, and the masers are the contours that you see here. And they approximately, you have to squint to try and work this out, approximately, and they tell me it's true, traces a spiral wave, which is how they think the protostar is getting fed from the disk that surrounds it. On top of this, we can also look at tidal disruption events. So looking at the emission from tidal disruption events, and we can also trace individual plasma blobs coming from other types of black holes in different regimes. This is the microquasar SS433. On the top, you've got the VLA and the low resolution radio with this sort of corkscrew effect coming from the precession of the black hole and its companion star. And then when you zoom in with VLBI, you can see the individual plasma blobs getting expelled from the accretion onto the black hole. And there's lots of other science that we can do with VLBI. We're not just stuck to this. We can map the structure of the Milky Way. We can trace via parallax measurements the different arms of the Milky Way. So you can see this here. The dots correspond to measurements. So this is in the Perseus. We've got the local Sagittarius arm, and we can use this to start mapping the structure of the Milky Way. And we can also use VLBI to track, or using Doppler tracking of spacecraft. So I think this one in the top right was when JUICE passed through the line of sight between us and Venus, and we were able to ping a signal and back, and the change of the modulation of that signal corresponded to conditions in the atmosphere in Venus. So we can do these sort of things quite cleverly to be able to actually get some science out of it rather than just communicating with these spacecraft using VLBI. And of course, VLBI, because of the extremely high angular resolution, we can start, as always, set the International Celestial Reference Frame. And we can do geodesy with this. So we can follow plate tectonics using VLBI stations and then work out how the plates are moving up and down over time. And because we need to know accurate positions of our stations, then we can flip everything the other way and actually work out whether we've got accurate. We can flip it the other way, and then we can see how our telescopes are moving over time. So you can see this perfectly here that we're still recovering from the ice age up in Northern Europe with the velocity of our telescopes moving upwards. And geodesy is really, really important. And I'm not a geodesist, so I'm not going to talk to you all for another hour about this. But it's becoming extremely important because it's integral for our GPS working. It's integral for many, many parts now in agriculture because you've got GPS controlled tractors and things like this. And because of this, the United Nations now have a geodetic center of excellence in Bonn. So this has just been set up back in 2023. So really, I always, whenever I was young, my dad always used to say, why are you doing astronomy? Well, it's this sort of stuff that, it's the offshoots of the things that I like doing can actually help people in the long run as well. And I like to think that VLBI can do this. Maybe it's just in my dreams sometime. Okay, great. So, I'm going to skip this. So the one things I wanted to talk about to conclude this talk is I wanted to talk about the next generation of stuff. So I apologize in advance if these slides are a bit more poorly put together, is the best word, because I was pulling this from last week's meeting. So you've got the cutting edge developments in a very poorly presented format. So though I wanted to talk to you about what's happening for the next generation of VLBI surveys and receivers, etc. And one of the biggest things that or anecdotes I want to use is we are expanding VLBI in multiple ways. So this is either we expand the bandwidths we're observing, so we can observe and collect more photons along a larger bandwidth, or we are expanding the number of telescopes, we increase the physical collecting area, or we're expanding the ways that we process the data so that we can actually do more with our data that we're getting in. So one of the big pushes recently has been these sort of ideas of either extremely wide bandwidth receivers or multiple receivers all working at the same time from the same reflector. So on the left-hand side here, you can see what has been proposed, or what is currently in use actually now in the Korean VLBI network. And these are 4 different receivers, which all can work at the same time. So this is a quad band receiver, which is developed for the Korean VLBI network. And this means that you can basically do 22 gigs, 43, 86, 129 all at once in a single observation. I used to have to ask them 4 different times and 4 different telescope proposals to do these sort of things. And by that time, my source that I was looking at has changed. So I'm like, okay, well, that was pretty useless. And this seems to be happening all over. So Yebes now has this tri-band receiver. So it has SX and another one, which I always forget, which is the third one. And this means that now we can observe these phenomena, and you can look at things in kind of a chromatic way at various different wavelengths. So this is an example coming from the Korean VLBI network. On the left-hand side, we've got the H2O masers, and then we got the silicon oxide masers at different energy levels. And these are all in a single observation. So you can do these maser maps all in a single observation. And because masers like to change very, very quickly, this allows you to start understanding what the region around this protostar is doing at that point. So this is rather powerful for being able to do these sort of stuff. The other thing that's useful is that having these extremely wide bandwidths means that you can get extremely sensitive observations, or you can map how the emission is changing across a large bandwidth. And this is really important for us in every single part of our science that we do. The other thing that we have now is this kind of push to not just widen your bandwidths, but widen the fields of view. How much of the sky can you see at once? So on the right-hand side, this is the ASCAP telescope. This is was the Australian precursor telescope to the Square Kilometre Array. And instead of having a single pixel feed, you just have a multi-pixel feed at the end. So this is what we call the phased array feed. And this allows us, instead of looking at a single field of view, which for the ASCAP telescope in this image on the left would be the red circle here, that would be all that you could see in one observation. We instead can see a much, much larger field of view here. So this is, I think, each one of these is about 4 moon widths across, if I remember right. So it's a few degrees across. And this is a really, really pertinent way, because essentially it means that you can survey the sky much, much quicker. It allows us to search for really, really rare transients. So if you're searching for where an FLB is, we can search a much larger area at once. If we're searching for a gravitational wave candidate, we can search degrees of the area of the sky at once, instead of with us just being kind of constrained to sort of half a degree or so. And this is because we've got these phased array feeds here. And for VLBI, there's a couple that are now working. The first one is on the Green Bank telescope on the left-hand side, the not falling down one. And this is the phased array feed that we'll be going on here. This will typically be at L-band. And on the right-hand side, we've got the phased array feed, which is at the top here. You can see this is basically them machining the demonstrator case, which will be for the phased array feed. This is from last week's conference when we were looking at what they were developing for this. And this will sit on the 100-meter telescope of Effelsberg, and essentially will increase its field of view from 7 arc minutes across at L bands to being over a degree across when we get the phased array feed on. So that's a very, very powerful way of us increasing our field of view and being able to search for these rare and wonderful events going on in the sky. So the other thing, this is kind of boring, but this is something that we need to do, is when we've got these huge receivers, with these new receivers, and we've got these very wide bandwidths, we want to be able to process the data. And we've got new backends coming. This widens the bandwidth that we can sample all at once. We'll digitize and then correlate. The first one of these is DBBC. This gives us about 128 gigabit per second of data, which is quite a lot. That would fill up your laptop in a few seconds. And we're now shifting to DBBC4. So this means we'll get a terabyte of data per second when we're only sampling the signal at 2 bits. So that would, that's quite a lot of data. And we've got the first prototype of this coming in 2025. And that means that when we're using these receivers, which go from 1.5 gigs to 15 gigs, we can sample the whole bandwidth at once and use that for science at once. And so that's extremely powerful. It allows us basically to surpass anything the SKA is going to do in the next 20 years, if we can do this. And to be able to process this, we're looking at new correlators. And correlators used to be pretty much a bit of hardware which multiply 2 numbers together. And now we're doing a terabyte of data per second on a correlator. And this allows us both to do the more complex experiments. It allows us to adopt more telescopes to mix the signals together to make better images. And it allows us to process the larger bandwidths. And this means we're going to get better, more sensitive observations. And just for context, when the square kilometer array comes online, the correlator, the supercomputer that will be used for the SKA, will basically be in the top 10 supercomputers in the world when it's made, because it needs to process so much data all at once. And you can see this is one of the new GPU chips that we're testing for VLBI correlation. And it's got a Grace Hopper chip. And I was astounded that it was passing data between the CPU and the GPU and then writing it to disk at a terabyte a second. So we actually have a problem. We have more of a problem keeping it fed than actually doing anything else. So we can't give it data quick enough for it to spit it out quick enough for us to process. But a lot of the VLBI correlators now also have these sort of supercomputers. So on the right-hand side, this is the long baseline array correlator at Pawsey Centre in Australia. And these are really, really flexible. Because they're so powerful, we can do a lot with this. And this is one area, at least in Pretoria, that we're trying to do. And we're looking at doing what we call new correlation modes here. This is something that I do personally. So I had to plug it in this talk. And a lot of the time, or one thing that we want to do is we want to start being able to actually look at the whole field of view of our instrument. Because in the olden days, VLBI had huge data rates. And so what used to happen is that people would essentially average their data down so that we can reduce this data rate. You couldn't put terabytes of data onto your laptop 10, 15 years ago, and you still struggle now. So what this ends up doing for VLBI is it ends up having this irreversible effect on all our images. And we call this smearing. So this is on the bottom left, you can see this is MVSS. So this is short baselines. This is with the very large array. And this is our kind of primary beam. This is sort of the field of view that we can see with our telescope. And in the center, we've got kind of a normal image and a normal image at the edge of the primary beam. But when we go to longer and longer baselines, these start getting distorted as we get to the edge of the beam. So in the center, it looks okay. But as we move further away, there has never, ever been a radio source that looks like a meteorite. And it points directly to the point that you're observing. So this kind of points towards here. And this is irreversible. It's because of the averaging of the data, the mass comes out. So whenever people, the last 50 years, have used VLBI, they've basically thrown away 99% of the data. So this is an example on the right-hand side. This is a image using the ASCAP telescope, that one with the phased array feeds on the ends. The white is the radio telescope field of view if I was doing a VLBI survey. But when I correlate the data and average it down, basically, I only get this field of view in the center. So all the information on all these other objects is essentially gone. Irreversible. You can't go back into the archive and go, I want to look at this source, because you'll image it and it will either be this or it will disappear. So what we want to do basically is correlate all of the data, and we want to look at every single one of these objects in the sky. And this is expensive, but now that we've got these new correlators with these really, really fast chips that we can't ingest the data quick enough into, we want to push it a little bit further. And we essentially mean that we want to do this for every single VLBI observation. And that means that in the next sort of 50 years or so, we should be able, not 50 years, in the next 2 years, we should be able to observe more sources than have been observed in the last 50 years since VLBI started. So this is hopefully what we can do. So watch this space in this area. That's just my own plug for my own science. I'm sorry, have to get it in. So yeah, and that hopes that we can find more of these gravitational lenses and win a Nobel Prize one day. And this is our first light from our correlator here. So this is a supermassive black hole at the top. It's only about 8 months old, and here's some nice supernova remnant in M82 that I got about 2 months ago, coming from our correlator. So what else is happening? Well, we've got new telescopes all around the world as well, coming into existence and being part of the VLBI collaborative environment. This is the Thai National Radio Telescope. Here on the right-hand side is the fringe, the correlated signal between the two telescopes in Germany and Thailand. And they have just joined a memorandum to join the European VLBI network. And this actually came from the currently deceased king's wish to get Thailand part of radio astronomy, basically. He was really enamored and wanted to build. There's a couple of more telescopes they want to build. And his daughter is basically spearheading this now and is really interested in astronomy. So yeah, the telescopes basically are going to be popping up everywhere. We've got China, Indonesia is looking at one as well. And of course, we've got Africa, which I'll talk about in a minute. We've also got the next generation Event Horizon telescope. These are a bunch of telescopes coming around the world. The new telescopes are all in red here. So there's one in Namibia, right near where I am, at Mount Gansberg. They've got new receivers, so they've got dual band receivers, and they're going to transfer the data now using space laser communications. Now that we've got these kind of network of satellites in the air, we'll use it to our advantage, because they used to wait over 6 months for the weather to die down so that the South Pole telescope could give their data to the ship and then physically give it to the correlator off the ship for the few petabytes of data that they've got there. So they're looking at basically using this space laser communications to move this. And now we've also got Meerkat. So Meerkat is our South African born and bred telescope, which is 64 antennas in the Karoo Desert in the Northern Cape in South Africa. And we recently got this to work with the VLBI array in Europe. And so you can see this kind of spike showing the fact that we've got constructive interference between our signals, between Effelsberg, Haselbeeshoek, and there's another bunch of antennas that participated, which aren't shown here. And of course, we've got the African VLBI network. This is a long story. It's something that us in Pretoria are trying to push. One of the telescopes is now active. So this is the Katunze radio telescope in Ghana. a 32-meter X satellite dish, which has basically been refurbished to now be a radio telescope. They've just got their maser, so they can now observe at C-band. And on the right-hand side, this was the original envisagement of the African VLBI network. And it hasn't really got off the ground for a couple of reasons. That there was a general unwillingness to sort of give money to telescopes, but also, some places they found that these conversions of large satellite antennas was more costly than they first thought. There's a lot more that you need to do to be able to see distant astrophysical sources than satellites, which are extremely bright. The other thing as well is the Kenya telescope got copper stolen. All the copper got stripped out of the telescope. So for now, the African VLBI network is actually sort of starting up as an idea again. Lots of people are instead of refurbishing their old satellites, they're looking at buying a square kilometer array dish and placing it in their country. And that makes everything so much easier because you're going to have the same receivers. You're going to have all the expertise from South Africa and nearby countries. And also, we've now finally got lots and lots of human capital in these countries through various different programs that we've had, which have essentially trained lots of students coming from Kenya, Mozambique, Madagascar, Mauritius, the SKA partner countries, and Ghana, who were then able to now operate these dishes. So that was really important, and that always takes a while. So essentially, I'm hoping in the next sort of 5-10 years, we'll start seeing more and more dishes appearing. I know we've got the African millimeter telescope now in Namibia, and there's now an SKA dish which will go in Botswana. And I'm currently trying to get Kenya to get a dish together because I'm going to be living there at some point. So I've got to keep my astronomy going, even if I don't do astronomy anymore in the future. And of course, we've got the square kilometer array. So I have to plug this because I'm the chair of the working group for this. And the square kilometer array, as you all know, is this super telescope, half in Australia, with these sort of Christmas tree shaped low frequency receivers, which all work together using software. And of course, the Pythagorean meerkat dishes, which will be combined with the SKA dishes, which are these kind of hexagonal shaped objects here. And the SKA, of course, has a huge remit. I think you've had talks on this before about what the SKA is going to do. And it's got sort of the broadest range of science of any facility. So this is going all the way from testing general relativity, looking at the first stars, magnetism, whether we're alone, etc., etc. And of course, me as part of the UKSRC, we're helping basically deliver this data and allowing the UK community to maximize their science. So that's what we're doing here is this sort of science regional centre. We disseminate, support, and also enhance the data products that are coming out of this telescope. Now, you may think, okay, well, we've got the SK, why do we need all these other telescopes around the world? And that's because the SK can't do everything. It says it's got the broadest range, but it is not all-encompassing. So this is a sort of diagram which shows this. What you're looking at here is on the y-axis, the bottom x-axis, we've got angular resolution. This is the resolution you get out of your telescope. And at the top, you've got physical scale at a redshift of 1, basically. And what this is showing is the bars are basically showing what that interferometer can measure in that region. So the VLA in its D configuration, which has a 2-kilometer longest baseline, can essentially measure angular resolutions of about 10 to the 3 to about 6, 7 arc seconds or so here. So 17 arc seconds, sorry, can't read my 10-2s. So that's basically what it's measuring, because essentially, if you remember from before, we've got an interferometer basically is a wholly lens, so we don't get all the information. Now, one key thing that sits here is that the VLBI instruments, email-in is kind of between the two, but I'll give it the benefit of the doubt, occupy this space at the top. So the only way that you are looking at things which are on physical scales like compact objects, which are on physical scale less than the kiloparsec, is by using VLBI. And you can see here, even with the SKA1, the SKA2 is a distant pipe dream, you still need VLBI for us to be able to look at sub-arc second resolutions, looking at these compact objects in distant galaxies. So we still need VLBI despite the SKA saying we can do everything. The only thing we might not need it for is if the Americans get their act together and make this monster of a telescope, which is the NGVLA. This is slated to be 2050, and it's an extension of the Very Large Array in New Mexico, and it will basically spread across North Mexico and a few other states, combining almost 2,000 dishes to work as a single interferometer. And what you're seeing on the right-hand side here basically is wavelength and frequency, angular resolution in arc seconds, spatial resolution, and it blows basically everything out of the water if this comes. But this is 20, 30 years ahead of us. So luckily the NGVLA has now been, I think it got approved in the decadal review for a design study. And so hopefully it might actually become a reality now, but this would be amazing to have. So I think that's the end of me talking. I've just seen my numbering has gone out. And I hope that I've sort of convinced you that the VLBI is still an important technique. It's used in lots of areas of astrophysics. Through the fact that it has extremely high resolution images, we can do cosmology, galaxy evolution, etc. But we're also expanding physically, i.e. more dishes, we're expanding frequency, we've got wider bandwidths, bigger fields of view, and this is all thanks to both novel developments in both hardware and software. If you're interested in more technical oriented developments, you can see the attachment, the link below, and this will actually send you to the conference and the proceedings from the conference that I was just at, in case you're interested more in the receiver technology and what we're doing in that area. And also, if you've got other questions, please feel free to contact me. I'm more than happy to speak at any time. So thank you so much for listening. Yeah, I'll take any questions if you got them.
Jack, thank you very much. We show our appreciation in the usual sort of Zoom way. There is a couple of questions in the chat.
Yeah.
One's about the older dishes being incorporated into these arrays and whether their physical limitations limit the whole network.
Yeah. No, it's a good point. It was one of the concerns with the Ghana radio telescope in particular, where they ended up having to essentially replace the whole surface, just to be able to even go up to 22 gigahertz that the dish wasn't accurate enough. So yeah, you've hit the nail right on the head here, because this is why a lot of the countries are going to just buy these new fabricated dishes, because it's so much easier to deal with than having to basically retrofit these things. Yeah.
I think you're saying it costs more to retrofit in time, trouble, and money than it does simply to buy another one off the production line.
Exactly. Yeah. And with with the SK and NGVLA, these sort of mega arrays are so much easier to just get an extra one added on. And it's cheaper. We've even looked at this for the UK array, the email-in array, of whether we could get a few more SKA dishes to complement it, because it's so much cheaper to do that at the moment.
Jack, is the profile accuracy still down to about 10th of the wavelength? Is that what you're looking at?
I think so. I don't know exactly what it is, because depending on different telescopes, they have different specifications. So I'm not 100% sure what they go to at the moment.
Okay, thanks.
No worries.
Are there any more questions? Either pop your questions into the chat or just unmute yourself and shout out.
I got a quick question. Is there anything for amateurs to do with VLBI, or has the technology gone so far away from us?
Well, it depends what you want to do. If you're on if you're trying to get them to work with your own telescope, it's probably a bit more difficult. But like in terms of if you want to have a go with messing with the data coming from VLBI telescopes, it's, if anything, it's more accessible now than it ever has been. So if you wanted to get your hands dirty and get the correlated data from a telescope, I've never seen so many sort of tutorials and workarounds and pipelines and things like this for you to get an image yourself from a archival data set or something like this. Because it used to be that VLBI was very experiment dependent. Like if something goes wrong, it completely changes the way you analyze or process the data. But nowadays it's a bit more uniform. There's a lot better standards in terms of how we process the data, and there's pipelines and things like this. I would never ever dream before the last sort of 5 years of ever giving a VLBI data set to any of my students, because it was like mental torture to give anyone VLBI data. But now it's completely changed. So yeah, if you're interested in getting into it, I've got plenty of stuff I could send you. And there's plenty of archival data which no one's ever looked at too.
Well, what I was thinking of, there are several amateurs now trying to get into interferometry using a couple of antennas in their large gardens if they've got them. But I was just wondering whether what the possibility of a couple of amateurs, a few kilometers or miles or tens of miles apart, being able to correlate their data.
I think it would be doable. Even the bit of software which does the correlation is fairly easy to run there. I'm more than happy to help out, because I remember one of the first in VLBI experiments was I remember a truck going around Manchester, right, with the satellite dish on the back, which was going with the 60-meter telescope, and they move away and they drive a bit further and correlate that data, and they drive a bit further and correlate that. Yeah. So I think it would be possible. You can always do this sort of clock searching in the data. I don't think you need a maser if it's a few kilometers at all.
Yeah. Okay. Thank you.
All right, there's another question in the chat. How much better VLBI angular resolution could be obtained with a receiver on the moon or Mars?
I guess it'd be a lot. Of course, I can't do the sum in my head at the moment. It's too late here to do that. But yeah, it'd be a lot. The biggest issue that we would have is actually trying to make a usable image of this. The main reason is that kind of if you're going to those sort of wavelengths, those distances, actually reconstructing what you think the sky looks like is a whole kettle of fish. It's very, very difficult to try and constrain that. I didn't really want to go into this talk because it's very counterintuitive, because the stuff you see within interferometers doesn't necessarily mean it's real. So not all of the time the thing that you see is real, which is extremely weird to say, but it makes it a lot more difficult for us to work out what's real and what's not.
Can I fire a quick question?
Please.
Sure.
Yeah, I'm going to ask a question about the square kilometre array. I know that's not the subject of your talk, even though you mentioned it briefly at the end. Why do they not mix the antennas between the continents of Australia and Africa, rather than have one lot on one side, so get the improved baseline?
Yeah, no, that's a good point. So originally they were going to be mixed at some band. So originally we had SKA survey. There was SK low, SK mid, SK survey, which is what ASCAP is, basically.
Yeah.
I think one of the reasons they didn't want the baselines to be too long is because the correlation becomes really difficult. So there's a lot more complexity in the correlation. So that means that the sort of supercomputer you need to correlate thousands of dishes together is going to be an order of magnitude more complex. This is also the reason why the SK is coming in these sort of stages. So we've got stage 1 where we go to 150 kilometers, And then stage 2 goes to 1,000 kilometers, and the jump between 150 and 1,000 doesn't scale linearly with the compute complexity. So it probably scales to the square or something like this, because you're starting to having to take into those accounts that I showed earlier for the VLBI correlator. So personally, it would have been brilliant for my science if they did this, but unfortunately, I think just complexity reasons, they started off small and expand outwards instead.
Would laser communications and satellites help more?
It would help to transfer the data, but not to correlate it.
No. Okay. Thank you.
No worries.
Any more
I
questions?
have a comment. Yeah, thanks, Jack. That was just incredible. Who knew you could run a VLBA backwards and do something completely different? That was news to me. Jack, looking at the data streams, it seems that there's vast amounts of data, and I was wondering if AI would be of any assistance, or if that's being explored in doing like a first pass on some of the data to help with the processing.
Yeah. So at least, so the main point that we would use these sort of AI/machine learning would be for the sort of discovery space, because a lot of the stuff beforehand is very, we know the maths, we know exactly what we need to do. It's just a matter of how much we need to do. So that's, for example, like the GPUs we use is because GPUs are good at multiplying an array of numbers with an array of numbers, and that's what a correlation is basically. But the machine learning/AI stuff has been particularly useful when we have these sort of large surveys where you've got hundreds of thousands of pixels, which you've got to look through and try and see if there's something there. Especially, there's been a lot of areas that a lot of this sort of stuff in what we call anomaly detection. So if you have one of those big images with lots of radio sources, essentially you look for the weird and wonderful things, because that might tell you something new about the physics that's going on. And AI and machine learning is really good at doing this. And it's good at saying, these all look the same and these don't look the same, so have a look at these. And then that takes you from having to look at 100,000 objects or 100,000 regions to looking at 10, which you can do. The other thing that the AI is actually good in terms of the telescope operations is in terms of RFI mitigation. So the radio frequency interference, if we can remove it before we correlate the data, we will lose far less data at the end. So there has been a lot of work which has been using kind of a machine learning algorithm to basically remove the RFI as it comes into the data streams before it can cause any damage. Because as soon as you Fourier transform RFI, it rings into all your data and demolishes it, basically. And in that link that I've got on the last page of my slides, there was actually a video showing this happening in real time with a machine learning algorithm, showing the RFI just being clipped out of the data and the clean data replacing the RFI, basically. So I'm sure there's lots of other applications for this in other areas, but it's,
Can you take out the data from Starlink satellites from by this technique as well?
We hope so. I don't think it's really been tested yet, but we really do hope so. It has been tested in one of the most difficult RFI environments, which is the center of India. So, so it has been working on the GMRT array rather well, and that, like, if you ever have any of that data and you want to remove the RFI yourself, just take away a few months of your life, because that's what I had to do.
Jack, I have another question. Are you thinking about using the way of citizen science in the future for the project? Because people have now access to fast network computers and things like that. And met hulp van AI and that type of things. I think also the citizens science community can help finding the basics and hand over to the professionals.
Yeah, it's in our back of our minds at the moment. We don't have the big enough data sets like the JWSTs do at the moment, but once we get it, we would definitely like to alleviate or use some of that. I was actually in a meeting today which was looking at a citizen science project for MICAT here in South Africa, the small connected interferometer, to look for the weird and the wonderful in their huge amounts of survey data. So yeah, you can either use machine learning, but people are really good at finding patterns too. So
yeah,
that's always good to apply it to. I see there's a question in the chat. Interferometry applied to astronomical radar imaging. Yeah, so there was, maybe I can put this in the chat. I think the VLBA can do this at the moment. So let me just I'll send you this this link. This is amazing. This is a image of the moon. There you go. So this is using the VLBA and the very long baseline array and the Green Bank telescope, using radar basically.
Brief pause while everybody pops it into their.
So it's got a 5-meter resolution on the surface of the moon using the VLBA.
Wow. Okay.
You can kind of see who the people why they would want to do this, because the VLBA is half owned by the military. I think they pay for half the time on the VLBA to do satellite tracking and sort of stuff. So you can see who funded the system, Raytheon Intelligence.
Okay. Any more questions? Because I'm going to leap in and have one of my own. How are these collaborations of telescopes organized? Do they have periods where they all come together, or periods where they split apart and do their own thing, or is it ad hoc?
It's a bit of everything. That's the best way to describe it. So the US one is easy and the Australian one is easy because the VLBA is the only dedicated one. So it does VLBI all the time. So that one basically will just observe a telescope proposal that goes in every 6 months. You know, we send in our proposals, we ask for time, and they say no or yes, and then we get our time. But for the other telescopes, so for the example, the European VLBI network, these are all individual observatories. They're all separate observatories most of the time, and so they will pre-organize basically blocks of time. So for the EVN, this will be 3 times 2 week blocks every year. They will normally have a block in June, August, and October and April. And that means all the telescopes will then be tied together to work as a VLBI array. The only other time that you ever get it is if there's something exciting goes on. So if we get a gravitational wave event, which is a neutron storm, so we're expecting an EM counterpart, an electromagnetic counterpart, we can submit what we call a opportune TOO, the target of opportunity. And then if the telescope agrees and the individual stations agree, as most of them will try and get online to all observe the object, and then we can correlate it later. So yeah, it's a bit ad hoc. It depends on the array. There's of course a lot of politics that goes along in the background of this, but yeah, it's a bit of everything of what you said.
There's another question come up in the chat. Is the CMB background a problem with the correlation?
I don't think so. I think it's mainly because it's not coherent emission, so it shouldn't come out in the correlation. It should just add to the system temperatures, I think. Top of my head, I don't know though. Be 100% honest.
Okay, any more questions? Yes, there's another one popped up in the chat. Left field question. You mentioned geodesy. Can these instruments detect a reverse time frame dragging?
Yeah, I'm not a geodesist, so I'm not sure. That's the most diplomatic answer to this. I'm trying to build a geodetic station in Kenya, so probably should know sometime soon. So yeah, you got me there, Richard. I'm stumped on that one.
Any more questions? I think we've got to the end.
Okay.
Jack,
Well, thanks so much.
thank you so much. And thank you for asking questions, just answering questions as they come up, because we have good set of questions. Your time is greatly appreciated. And I think it's just a wonderful thing about Zoom is you can join us from South Africa with people from the middle of the Pacific, the States and Europe, all for a talk on a Monday evening. I think that's absolutely wonderful. Thank you very much for your time. And thank you, everybody.
Thank you all for listening.
For coming.
And if you do have other questions, please do email me. I'm more than happy to take them. So yeah, thanks so much. And thanks for the opportunity. Take care, everyone.
The notice for the next session will be out in due course. Thank you very much. I'm going to stop the recording, which means no more questions.